Okay, so this video is going to conclude our discussion and supplement for Module 4A, which is talking about the scientific study of problem solving. And in this particular video, I'm going to talk about a type of problem solving called analogical problem solving or analogical encoding, as it's sometimes referred to. Okay, so let's go ahead and start our discussion of how people use analogies to solve problems. Okay, so the last problem I asked you guys to solve was the radiation problem. Okay, so the problem says, suppose you are a doctor faced with a patient who has a malignant tumor in his stomach. It is impossible to operate on the patient, but unless the tumor is destroyed, the patient will die. There is a kind of ray that can be used to destroy the tumor. If the rays reach the tumor all at once at a sufficiently high intensity, the tumor will be destroyed. Unfortunately, at this intensity, the healthy tissue that the rays pass through on the way to the tumor will also be destroyed. At lower intensities, the rays are harmless to healthy tissue, but they will not affect the tumor either. What type of procedure might be used to destroy the tumor with the rays and at the same time avoid destroying healthy tissue? Okay. So students often have a lot of difficulty solving this problem, right? So what is the solution to this particular problem? So the solution to this problem, which less than 10% of people came up with in the Gick and Holyoke 1980 study in which this problem was presented, is simply to bombard the tumor in the center with a number of low intensity rays from different directions, right? So basically converge upon the tumor with a bunch of low intensity rays, and what that does is it destroys the tumor from the center outward, and because all of the rays are low intensity, you don't have the problem of damaging surrounding tissue. So interestingly enough, a medical technique that's utilized in the treatment of brain tumors called radiosurgery uses the same procedure, right? So you eradicate brain tumors by converging a number of different gamma rays on them, or gamma knives, I think they're called, and that destroys the tissue without damaging other regions of the brain in the process. But as I said, it's very, very difficult. So Gick and Holyoke found that, like I said, less than 10% of people were able to solve the problem when they were given the problem by itself. Right? So one of the things that they did in subsequent experiments is they gave them another problem before the radiation problem, right? So the problem that the second group of participants was given first is something called the fortress problem. So the fortress problem says, suppose you are a general trying to capture a mighty fortress. The fortress is at the center of a country that has 5 roads leading into it from different regions. Each of these roads has been mined to defend against large attacks, but to allow for small parties of farmers to travel safely. The mines will explode only if 3,000 or more people are on the road at once. In order to capture the fortress, you need to bring your entire army of 10,000 people to its walls at almost the same time. If the soldiers arrive too gradually, the smaller groups will be defeated by the fortress's defenders. How can you bring the whole army to attack the city at once? Well, the solution, right, is identical to the solution for the radiation problem. So the solution is to send small groups of soldiers down each of the roads, coordinating their movements so that they all arrive at the fortress at the same time. Right? So just like we're using small intensity rays to converge upon the center of the tumor, we're sending small groups of soldiers to converge upon the fortress. Right? And when participants were given this problem beforehand, right, that number of 10% increased to 30%. So in order to get a significant proportion of participants to solve the radiation problem successfully, they not only had to see a problem with the same solution, right, but they had to be told that that solution is relevant to the radiation problem. Right? So just giving people the problem isn't significant. You have to reveal to them that the solutions are analogous, or that the structural features of the problem are analogous. Right? So now let's turn our attention to what cognitive processes are happening when people attempt to solve the radiation problem using the fortress problem as an example. Okay, so this process of solving one problem using the same technique that you learned on an earlier problem is called analogical transfer, right? So with analogical transfer, once you identify the solution to one problem, you can utilize the same technique on future problems provided the underlying structure is the same. So what analogical transfer requires you to do is reason from the previously solved problem called the source problem, in this case the fortress problem, to a new unsolved problem called the target problem. Right? So the source problem is the fortress problem, and the new target problem is the radiation problem. So what are the specific processes that you have to go through in order to transfer the solution to the fortress problem to the radiation problem? Well, first, you have to notice that there's an analogous relationship, or you have to notice that those problems are similar to each other, right? So noticing that there is an analogous relationship between the source problem and the target problem. This step is obviously going to be really crucial in order for analogical problem solving to work. However, as we've seen, or as I've talked about, most participants need some kind of prompting before they notice the connection between the source problem and the target problem, right? So Gick and Holyoake consider this noticing step to be the most difficult of the three steps, right? And a number of experiments have shown that the most effective source problems are those that are most similar to the target problem, right? So when I say similar, I don't mean just similar in terms of the underlying or structural features, but also the surface features, right? So one of the things that's difficult about reasoning from the fortress problem to the radiation problem, right, is that the topics are totally different, right? So the solution is very, very similar, but the objects that you're thinking about are very, very different. So subsequent research has shown that the best analogical transfer happens when the objects or the kind of the physical features of the source and target problems are similar to each other. Okay, so next you have to map the elements between the source and target problems, or you have to map the correspondence or similarity between the source problem and the target problem, right? So to use the story to solve the problem, the participant has to map corresponding parts of the story into the test problem by connecting the elements of the source problem, okay, to the elements of the target problem. So let's look at that a little bit closer. So if we were successfully mapping the elements across these two problems, we would see that in the first problem, the fortress corresponds to the tumor, right? This is the object that you're converging upon. The mind roads are going to correspond to the surrounding tissue, right? So these are both very fragile things, right? So the mind roads can only hold so many soldiers before they blow up, and surrounding tissue can get destroyed even at very, very low intensities. And the attacking troops, right, is that converging process. So bringing many, many troops together down the mined roads, or bringing many, many low intensity rays together, right? So the small groups of soldiers are going to converge upon the fortress, and the weak rays, or the low intensity rays, are going to converge upon the center of the tumor. Okay. And lastly, once you have successfully mapped each of the elements from the source problem to the target problem, you obviously need to generate a solution and apply it to the target. Okay, so applying the mapping to generate a parallel solution to the target problem. So this would involve, for example, generalizing from the many small groups of soldiers approaching the fortress from different directions to the idea of using the weaker rays that would approach the tumor from different directions. So noticing and mapping, like I said, are arguably the most difficult steps in analogical problem solving. Okay. So let's go ahead and look now at the data obtained by Gick and Holyoake, just to review. Okay, so again, like I said, when no hint was provided, when they were given the radiation problem by itself, less than 10% of participants solved it. This number jumped up to 30% when they were given an analogous problem, but they weren't prompted that the fortress problem could be used to help solve the radiation problem. And we got a little over 70% of participants to generate the correct solution when the fortress problem was provided with the explicit instruction that they could apply the same solution to the radiation problem. Okay, so in general, like I said, participants do not produce corresponding solutions with any great frequency unless given a hint, right? So these results demonstrate the difficulty of recognizing the relevance of one problem and its solution to another, right? So analogical transfer is very, very difficult, at least that's what laboratory studies would suggest, is that we're not very good at using analogies to solve problems and noticing correspondence or similarity between problems. Okay. So what are some ways to optimize problem solving? So remember I told you guys that cognitive psychologists are interested in developing interventions that make problem solving more efficient or more effective. Right? So I'm going to show you 2 experiments that illustrate how we can help people with analogical transfer. So in this first study, participants were given 2 sets of instructions, right? So participants in one group were told to analyze a series of algebra problems one by one, okay? And another group was instructed to compare each of the problems to each other, right? So one group solved the problems and the other group simply compared the problems to each other, or attempted to notice what the problems had in common, right? So this is an example of that mapping procedure. And what they found is that when participants were given new problems later on, those who had been forced to consider what the problems had in common, because they were thinking about the underlying structure of the problems, right? So they were ignoring the surface features and rather focusing on how the problems might be solved. Okay, they were better at using those same problems to solve new problems later on than participants that had just worked to find solutions to the problem, right? So anytime we can think about a problem in terms of its underlying structure, kind of ignoring those surface features, the more successful we're going to be. Okay, another example, participants were again given problems, and one group was told to memorize the problems. So memorize the features of the problem and the solutions to the problem. Another group was told to work on understanding the solution and understanding it well enough that they could teach it to somebody else. Okay, so the people that were told that they were going to have to prepare to teach someone else the problems were able to solve 90% of brand new problems successfully, right? So again, they're transferring what they learned about the underlying structure of the problem. And this compared to memorizers, right, who were only able to solve less than 70% of the new problems successfully, right? So again, this illustrates the importance of not getting stuck on surface features, but rather thinking about the deeper structure of the problem. Okay. So one final thing I wanted to note is that psychologists haven't just focused on solving problems in the laboratory. They've also looked at more naturalistic or real world settings in this domain, right? So they've looked at, for example, scientists and inventors and watched them as they're engaged in conducting experiments or developing products to see how they solve problems kind of in the real world, right? So the advantage of this is that it's much more akin to what actually happens or how we actually use our cognition. So it has really good external validity, right? But the disadvantage is that it's very time consuming and it often costs money, right? People don't let you just kind of show up at their lab meetings or their place of business unless you offer some kind of monetary incentive. And it's also got the main drawback of naturalistic studies from a scientific perspective, in that we can't really isolate or control variables or manipulate anything. So it's lacking what we call internal validity. But one of the things that becomes very, very obvious is that while people sort of characteristically are struggling to solve problems in the laboratory, right? So we see this absolutely in the Gick and Holyoake experiments, but even before we were talking about analogies with functional fixedness and mental set and so forth, right? So all of these experiments lead us to the conclusion that we must be really, really bad at problem solving. But in fact, all of the naturalistic or real world research seems to suggest that we're actually really, really good at problem solving. And particularly, the use of analogies seems to be quite common, and even as a characteristic feature of the process of discovery, right? So the process that scientists and inventors go through, right? So in one case, they looked at molecular biologists and immunologists, and they videotaped them during their lab meetings. And they found that when they counted the number of analogies that the researchers used per hour, that they used 3 to 15 analogies in just the span of 60 minutes, right? So for example, if E. coli works like this, maybe your gene is doing the same thing, right? So just like we use maybe the solar system as an analogy for subatomic particles, right, and so on, analogies seem to be particularly effective in the process of scientific discovery. Similarly, they also looked at engineers and how they develop new products, particularly those with medical applications. And they found that in the span of an hour-long meeting, engineers often propose an analogy every 5 minutes, right? So again, what this illustrates is something called the analogical paradox. And that is that universally, in a number of different laboratory studies, we seem to have a lot of difficulty solving problems that require analogical transfer. So we have a lot of difficulty generalizing from a source problem to a new target problem. But in reality, particularly during the process of discovery, right, people do tend to use analogies quite often to aid other people's understanding or to propose new theories, right? So all that is to say, even though the laboratory evidence suggests that we're very poor at problem solving at times, we are very effective in the real world, just like scientists and inventors and engineers. And me as a little girl with my markers, right? We all have really an astonishing capacity to all sorts of advanced cognition in this domain when given the opportunity to do so. All right, guys, so that concludes our discussion of problem solving and our last lecture for the semester. So thank you so much for hanging in there with me. I hope these videos were helpful and I hope they made sense. And certainly if you guys have any questions, as always, feel free to reach out to me. Okay? Have a great day.